We got that on video though, right there. Actually, the mic's right there. So we'll see how this goes. All right, my little friends. Well, and some of you are a little bit larger than others. Oh crap! You guys might not be aware, but I do know that 64 ounces of Mountain Dew on this floor makes a huge mess. Huge mess. That was a good save. All right, here we go. First off, what's the total mass of N2O5?
108.
108. All right. What's the mass of just the N2?
28.
28. So we take 28 divided by 108, multiply it by 100, and it equals?
26 somehow.
Math magically. It becomes 26%. Who had that answer? Raise your hands. Or with some decimal number. Really? What did everyone else have?
I didn't throw it already.
You what? Well, don't do it wrong again.
Alright, I wasn't even doing the equation.
Jordan, what did you get?
I got 24%.
24%?
The atomic mass of oxygen is 16, right?
Yeah.
How do I get a different number?
I don't know. While he's doing that, let's do this one. Who thought this one was harder? Oh, okay, fine. Only one of you. It was a little harder because it was supposed to be harder, I should say, because you had to find the formula from the name. Copper 2 oxide. So Cu is what charge? Plus 2. What's oxygen? -2. So I tried to make it pretty easy. Does this add 0? Yes, it does. So it's just Cu and O, correct? What if you screwed up and had Cu2O2? This one, it wouldn't matter. Way to screw up and be right. It's always fun. All right, so here we go. Copper has a mass of 64. It's 63.5. It's okay if you use 64, but copper, typically, we round it to the 0.5. 63.5 over 79.5, is that right? And if you didn't do the 0.5s, will be a little off from each other, but that's okay. So you divide this, and I don't remember, 80? We got pretty close to 80%. Raise your hands. Steven, what'd you get? You couldn't remember how to do it?
Yeah, I've done it before.
Did you get number 1 wrong also then? Okay. Can you remember how to do it from now on? I'm committing you. Okay. Are you okay with just basic percent? All right. Today, by the end of the day, I'm going to give you a percent, and you're going to find me a formula. Okay? That's all we're doing at the end. We're going backwards. And it takes a lot more effort, but strangely, people enjoy it because it's a little bit hard, but really easy. So you're like, whoa, I did work that was super easy, like hiking to the bee. You're like, wow, I hiked all up here. I feel so good about myself. When in reality, like, you could have thrown a rock as far as you hiked. Okay, not really. And I shouldn't talk. I hate hiking, and I've never been to the bee. It's too far. All right, here we go. That's another example. All right. Let's talk about moles. Okay, so here's our introduction. We've talked a little bit about moles, but just know the following. Moles equals big number. I've already told you that, right? In fact, a mole is equal to this number. So 1 mole equals, I'm going to write it down here, 620,000. All right, I got to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. It equals that number. So if we said that sodium had a mass of 23 grams, it'd be per every one of these atoms. Well, who wants to write that? Raise your hands. Okay, no one wants to really write that. So, instead of writing that big freaking number, we just write the four-letter word of M-O-L-E. You can put an S on it if you feel like it. It's America. But that's all that we're going to do. So we're going to say moles. Moles is just a word, like a dozen. It just means a number. Okay?
You say that number.
Killing me. All right. Now, here's what's super important. Let's just do this basic reaction. H2 plus Cl2 goes to 2HCl. You okay with that? I'm going to change this to blue just for fun. That's ugly. 1, 1. Moles. These numbers we've been putting, they are actually moles. So when we say 1H2, we don't mean 1 H2, we mean 1 mole of H2 plus 1 mole of Cl2 makes 2 moles of HCl. Okay? Coefficients are just simply moles, or molar ratios, or molar proportions, or whatever else you feel like saying. Moles is our way to compare something to something else in chemistry land. So, for instance, have you ever heard the saying like, that's comparing apples and oranges? All right, apples do not equal oranges, right? They have different everythings. But could you compare the cost of apples to the cost, I tried to get that OCD people, of oranges? Could you compare these to each other? Yeah, how come? Are you talking about an apple or an orange anymore?
No, a number.
You're talking about money, right? We've converted them into money. So dollar signs is a way that we can make a direct comparison of apples to oranges. All right? In chemistry, moles are our dollar signs where we can make our comparisons between moles of H2 and moles of Cl and all that stuff. You're the best.
Can you think that person in your class right now?
Oh.
Just give it out now.
Natasha, yeah. Yep, thank you. Look at them telling me how to live my life. What if I don't want to give it out until right now?
Oh, well, thank you.
Yeah, I'll show them. You're welcome.
You can have your stick note.
I don't need it.
You sure?
Put it on Shakespeare's head. All right. Okay, is everyone all right just kind of with that little analysis, or analogy, I mean? Okay, we can't compare them to each other unless we get them both to moles. Okay? Now, just one little teeny extension of that. Apples and oranges, and your H2 and Cl2, like what we're trying to say here is, if we had the mass of H2, would it equal the mass of Cl2? Not even remotely close. This would be 2 grams. This would be 71 grams. So we cannot compare their masses to each other. but we can compare their moles because it's both in the same unit now. Like everything has been taken care of when we convert things to moles. Okay, it's a really, really important thing that you kind of have a decent grasp on what we're talking about when we talk about moles. Okay? All right, all else fails, think about it that moles is dollars because almost everything in this world can be quantified to its value, and we do that all the time. Next up. Okay, Avogadro's number, that's just what we've been talking about. Avogadro is the one that discovered this number by working with gases. Gases, if that's all right. And he found out that the same, like a mole of something always related to the periodic table, and in gases, a mole of something always occupied the same space. I feel like I already wrote that. This is all I was saying before. Coefficients are molar ratios or molar relationships or molar proportions. So just one more reminder. We could use it to compare H2 to HCl. It would be a 1-to-2 relationship. Or if you went the other direction, it would be a 2-to-1 relationship. Easy enough? Okay. Now, these are the mass of 1 mole of a substance, i.e. grams per mole. The molar mass of an element is the mass number for the element that we find on the periodic table. The formula weight in AMUs will be the same number as the molar mass in grams per mole. Okay, all we're saying is when you look at the periodic table and it says carbon has a 6 and a 12, the molar mass is that 12. Now, I write it kind of funny, and it might bug you, but I write 12 grams per 1 mole. Okay? Because I'm lazy, and writing on the plate and picking up and moving requires too much time. Is there a splashy here? Sure, it's there. Oh my gosh, people. Come in, my friend.
Yay.
Thank you so much.
You're so welcome.
See how fast it went from angry to nice? I learned that from my mom. She'd yell at us and then answer the phone. Like, yeah, I'm a perfect Relief Society president. I would never yell at my kids ever. For some reason, this once in a while cuts out on audio. Has anyone even watched one of our class videos yet? I feel like I make them for nothing. Oh, there you go. Okay, thank you. You don't have to. You really don't have to, but if you miss a day, and I don't do it every day, but if there's like a longer lecture day where I know we're doing something that might be hard, I usually record that. I want to get to the point where I record every day, but sometimes I just forget. All right. Are we okay with that? Okay, mole relationships. I'll put this in English after we read it. It says that 1 mole of atoms, ions, or molecules contains Avogadro's numbers of those particles. 1 mole of molecules or formula units contains Avogadro's number times the number of atoms or ions in each element in the compound. Okay, what? Well, this. What this is saying is that 1 mole of sodium contains that many atoms of sodium. 1 mole of sodium oxide contains 2 moles or 2 Avogadro number atoms of Na and that many atoms of O. So it's just saying, go ahead.
Oh, I was just going to say, is that basically the same thing for like compounds that's saying it contains 1 mole of that compound?
Yep, it's exactly the same thing.
So like there are 6.02 times 10 to the 23rd of the molecules of Na2.
Yep.
Oh.
Yep, so we have this many total atoms or 6.02 times 10 to the 23rd molecules of Na2O. Come on in. You're welcome. What's that?
This is not on you, this is for me.
Where you have like
It's fine.
H2, is that going to be that many numbers of just H or that many numbers of H2? Do you understand my question?
It would be either that many of H2 or twice as many of H. It could be defined either direction, it won't matter.
Okay, that makes sense. Thank you.
Okay, yep. All right, are we kind of all right with that one? All right, it's just a bunch of numbers. We don't write 23 zeros because that would take a lot of work. Carpal tunnel, it's real. So we just put mole. All right, finding empirical formulas is math that is not hard. I promise. Most of you, in a very real nerdy way, will feel that this is okay. I don't really know how, but in the end, when you get the right answer, you're like, wow, I did sign up for this class for a reason. It can be strangely fun. Like, how do you pronounce Sudoku? Whatever those things. Thank you. All right, so here we go. Finding empirical formulas, when you look at this slide, might seem very intimidating, but I swear to you, you're going to enjoy it. Well, okay, I can't promise you that, but it won't be that bad. All right, one can calculate the empirical formula from the percent composition. So what we're going to do, I'm going to give you percent. This is slowing down. I'm going to give you percents. You're going to make them grams. Then you're going to make them moles. And then you're going to find their ratio to get their empirical formula. Okay. Now, if I just said go, then you would feel like you're in a college class. But we're not in college. So let me hold your hand a little while and work through these. So here we go. Who's ever heard of PABA in your sunscreen? Raise your hands. PABA. Anyone ever seen it? Well, okay, I love you, but you're dumb if you're not looking. If you don't have PABA in your sunscreen, then you are buying useless stuff that you might as well just pour water on yourself. PABA is actually the stuff that keeps you safe. Para-amino benzoic acid. Sound fun? All right. So what you do is it's made up of these percentages of their elements. Now be careful when you read these that you put the right element with the right value. So the very first thing that we do is we convert, write this down if you're a note taker, to grams. And you're like, well, how do you do that? Well, this is literally the easiest math we will do all year on this step. I promise you, every single one of you, no matter what math teacher you have, can do this. All right, here we go. So did everyone write convert to grams, step one? All right, so carbon. What percent does it tell me is carbon? 61.31. Okay, listen. If I have 100 grams of stuff and 61% of it is carbon, how many grams do I have of carbon? 61. I knew you could do it. So all you write is 61.31 grams and then put carbon. Just C. Now be careful. I have hammered into your brains that the next elements are diatomic and they are in a chemical reaction. Am I writing out a chemical reaction? No, I'm finding the formula of something that already exists. So I know that you love chemistry and you love when I teach you one thing and say don't use it now, but we're going to do that. Same thing, no penalty kicks in volleyball for using our hands to hit the ball, right? Different sport, different rules. Are we balancing chemical reactions? No, so different rules. Here we go. So maybe you've already figured this out, but how many grams of hydrogen? 5.14 grams of H. So what I was saying, don't put the 2 right here because we're not dealing diatomic land. We are finding a formula of a compound that already exists. All right, then nitrogen, we have 10 point something. Is that right? 10.21 grams of nitrogen. Remind me that's a 2-1, not a 4. I know it kind of is ugly. And 23.33 grams of O. Okay, raise your hands if you can do that step. essentially you take your percent sign and turn it into a G. That's pretty simple math. And it should make sense. Once again, we're just going to assume we have 100 grams of whatever we're talking about. Well, if we know the percentages, then we know what we're talking about. It's very simple. Okay, next step requires a teeny bit of math, but nothing hard. So we convert to grams. Then the next step, let's switch colors here. The next step is to convert to moles. Now that might sound intimidating, but converting to moles is simply dividing each one of those values by their molar mass. Where do we get their molar mass from? Periodic table. You tell your lab partner what C is, they tell you H, they tell you N, and you tell them O. Go. Discuss. Quick. I need a drink. Okay, did anyone say 28 for nitrogen? No, good. When would you say 28 for nitrogen? If it was diatomic, but we're not in diatomic land right now. Okay, so I'm going to divide each of these by their molar mass. Noah, what was carbon? 12. There's 2 Noahs in this class? I didn't know that. Steven, hydrogen? 1. Gibby? Nitrogen? 14. All right, we're good. Christine, oxygen? 16. All right, so converting to moles, it's a fancy way of saying divide by their molar mass. Get from the periodic table. And do me a favor, like this hurts me to the very core. Don't ever choose the wrong number in the box of the periodic table. Don't put 8 for oxygen. Someone is going to do that on the test, and I'll have to pray about being friends with you ever again, but I doubt that I will. Don't do it. All right, so now we have some numbers. Watch how good I am. This is 5.14. Yeah? I'm pretty good. Hey, this is also almost 5.14. And this is 0.7 something. 7.2? What is it? 7.3. And I don't know what this one is. 1.5? How about 1.46? Just go with me. I want it to be 1.46. All right. Now, remind me that's a 4. So we've converted to grams, we've converted to moles. Now the last, well, there's 2 steps, but really only just 1. The next one is pretty simple. Divide all answers by smallest answer. I might have the wrong term. Correct me if I'm wrong, Mr. Rasmussen. You're a math teacher. But I believe all of these are going to be divisible by that number. So would we call that the lowest common multiple?
It's a factor.
Okay, the smallest common factor.
That's a factor. You don't know if it's the greatest common or the smallest.
Okay, well, fine.
Yeah, it divides into everything like it's a factor. To be a multiple, it has to be at least as big as the biggest.
Okay, so it's a factor. Thank you. I feel smarter. All right, so all we're doing is we're finding out what these are all going to be when we divide them by the smallest value. I'm pretty good at math right here. That's a 1. I can do this one too. That's a 2. And I think, was this 7? And they should all be pretty close to whole numbers if you did them in your calculator. And when I say pretty close, I mean like 0.08 or 0.02 or 0.01, even better, or 1. Okay, so we did all this math, and it's like going to the grocery store when they add it all up and it comes to like $28, 0, 0. You're like, that doesn't ever happen. Well, we did math and we got whole numbers. That's weird. There's a reason why. The final thing we're going to do, this video is going to be amazing. The final thing we do is write the formula. So what do I mean by writing the formula? These numbers right here are the subscripts. We did all that math simply to find the subscripts, so it's going to be ugly. Oh, well, I'm going to write it really low. So it's C and what little number? 7. H and what number? 7. O and what number? Oh, sorry, N was next. You should go in order that it lists them, by the way. NO2, right? And I'm done. I'm done. Kind of a little bit chemistry, kind of a lot mathy, but really not that bad. Yeah.
If it's an acid, wouldn't the H come first?
Kind of. Thank you for calling me out on that. Yes, it would, except we are an organic acid, and they don't fit any definition of acid you've ever seen before. You're welcome. I love you too.
Another exception.
Yeah, but you don't have to know organic acids. But that was great application of what I taught you, but you don't have to worry about that. Who can do this? It's forced. Repeat them every time. You ready, set, go. Holy cow, that's what happens when you don't check your email.
Between an empirical formula and a molecular formula.
Okay,
Probably
well,
in the reading, I just
it is in the reading, and we will talk about it. The empirical formula is the lowest possible ratio, like
Okay, and then the molecular
H2O.
is what it actually
Right.
is. Okay.
So if water was H4O2, this process would not work unless we add something like this. We would have to know the molar mass of the substance to make sure we knew it for sure. You're welcome.
We're learning how to use some tools here, so we appreciate
Sweet.
it.
Lunch is in my room today.
Thank you. I'll be there.
I don't want.
Oh, right, yeah.
Okay. All right, who is already done? All right. Give about one more minute. got the numbers. 1.5. Thank you. You're the best. Okay, who had SO2? Okay. Now, here's why we got to get things to moles. If you just look at this formula and you're a non-educated chemistry kid, you'd say it's 50% sulfur and 50% oxygen, so they must just be SO, half and half. But not true, right? Because we can't compare apples and oranges, but we have to compare the price of apples and oranges, the price being the moles. That's where you turn out that it's a little bit different than you would expect. And this makes sense that it's a 2-to-1 and it's 50-50 because one has twice the molar mass as the other. Okay, a harder one. Uh-oh, there's the answers, so I better just clear all that out. Okay, here you go. This one has a wrinkle that makes it a little bit harder.
So is that in grams?
Yeah, these are the grams.
So do you want the same thing?
Yep, same process. I'm looking for the formula here. Now, this has a problem. We'll see if
You gestured to me when you said problem.
Christina's a problem. Oh, wait, whoa. No, this one will have, it'll have a wrinkle, which chemistry's full of wrinkles. It's like it sunbathed its whole life without sunscreen. Now it's 40, but it looks 85. Really. Mm-hmm. Has anyone come across the problem yet? Yep. So the oxygen's a problem, right? Because it doesn't come out to a whole number. It comes out to what? 2.5. So,
Like, times to a number?
Yeah.
And make it to a bigger number times all.
that's what you have to do. Okay? If you are given a number that doesn't easily round, and those are usually 0.2, 0.3, 0.5, like 0.333. All those are pretty easy, or did I say 0.25 also? All those are easy, either multiply by 2, 3, 4, 5. So this one you're at 0.5, 2.5 times 2 is a whole value. So every number you get has to now be multiplied by 5 to fix that. Or by 2, sorry. I'm an idiot. What am I doing? I am a real idiot. Ooh, you know what? Just undo everything you did, and you should have all the answers. Boom. Something bad, yeah. Okay, C14H18N2O5. Who had that? Okay, good. Let's do one more example where it is a empirical versus molecular formula. Who has no idea what that means? Okay, I'll explain it. This was in the notes upwards of a week ago, so you can't be held accountable for that, right? That's past information. It had to go out that ear to make room for what was coming in this one. So an empirical formula is the lowest ratio, that's trying to say lowest, whether it does or not, of elements. So that would be like CH2O. Do you remember this? But the molecular formula, because this is not a thing, the molecular formula is what it really is. So H2O in reality is sugar, C6H12O6. The process that we've been doing can only find you that. It cannot find you this. So there's a problem. So what if I am decomposing sugar? Well, if you're decomposing sugar, they're going to give you one other piece of information that they can find, and that's what the mass of the molecule is, or the molecular weight. With me? Okay, so let me find this example. I have it on one of these things. That's not it. Oh, that's that thing. Huh, haven't seen that forever. Where? Oh, right there. We'll see if this is it. This is just problems from an old test. No, that's not it either. I will find it, I promise you. Okay, here we go. No, never mind, we can't do it. It's a different process. All right, well, let's just go back to one we've already done that was pretty simple. So, well, let's say we had PABA. We got to do some math here. So I'm going to add up this molar mass here. So what we got? 84, right? Plus 7, plus 14, plus 32. $123? Yeah. You sure? 137. What are you laughing at? Okay. Okay, so this is what PABA's mass is for real, but the test question that I can't seem to locate right now, I thought that would be it, but the real test question you'll have will give you the information, then it would say that the mass is 274 grams per 1 mole. So when this happens, what you do, if it gives you the mass, you still do all the same stuff, and then you find the mass, and it will always be a factor of that value. So if this was true, the actual molecule would have been C14H14N2O4. You with me? We'll find the one from your homework, and we can do it real fast.
So basically, we find the molar mass of the empirical formula, and we can multiply everything. It will be a factor of the molar mass of the actual molecule.
Mm-hmm.
That makes sense.
Okay, ibuprofen. You ready? Ibuprofen is in a lot of medicines you take. It has 75.69% carbon, 8.8% H, and 15.51